Today we're going to cover two more tests, the integral test and the P-series test. First off, the integral test, and this is on page 216 in your book, the conditions that must exist in order to use the integral test are as follows, and you need to state these. The function f of x needs to be positive, continuous, and decreasing for all x values greater than or equal to 1. And so what the integral test says, if these conditions exist, that the series a sub n and the integral of f of x, if we use the a sub n as f of n, that's basically what we're saying here, either both of these will converge or both of them will diverge. Essentially what we're going to be doing is we're going to take the integral from 1 to infinity, an improper integral, because one of our limits of integration is infinity. And based off of what we get from there, whether it has a limit or does not, that will tell us what this series is. In other words, if this has a limit, then this will converge, because something that has a limit is saying that it converges. If it does not have a limit, meaning it's infinity or does not exist, right, that means divergence, which means this will diverge. It is not by any means saying that these two things are equal. That is not what this test is about. It's just saying, okay, let's see if this limit, because in order to integrate this, it's going to be a limit. That's where the improper integral piece comes from. If this is convergent, this will be convergent. If this is divergent, this will be divergent. That's all it's really saying. All right, so here's some examples. We'll go through all three of these. And first we need to test for, make sure that they're positive, continuous, and decreasing for x greater than or equal to 1. And so one of the things that we know is that this is definitely going to be positive no matter what value. I'm going to plug a positive value in for n. This will make this whole thing positive. It's not going to have any holes. I can't make this bottom equal a negative. This will always be positive on the bottom, and therefore, since there are no holes, it's continuous. And the numbers on the bottom are going down as n goes up, which means the fraction itself, its value is decreasing. So we've met those conditions. And so f of x, in this case, this 1 over n squared plus 1, is positive, continuous, and decreasing for all x values greater than or equal to 1. So what we're going to do is we're going to take the improper integral, we're going to integrate that. Okay, and to integrate that, since this is improper, we're going to take the limit as b approaches infinity from 1 to b of 1 over x squared plus 1 dx. And if this limit exists, then we know this series converges. If this limit does not exist, then we know that this series diverges. Okay? So think about this. See if you remember one of your tricks to come up with the integration of this. Pause it if you want. All right. Hopefully you've had a chance to figure that out. Anyway, this is the arctangent. Okay, that's the form that it's in. We're going to integrate it from b to 1. And of course, if you recall, the arctangent goes from negative pi over 2 to pi over 2. So as b approaches infinity, this whole thing will approach pi over 2. And then the arctangent of 1, that's a 45 degree, which is pi over 4. And so it's pi over 2 minus pi over 4. We don't actually care what that is. That value doesn't matter. But there's a value, right? This is a number. And, of course, it is pi over 4. But that's not what we're worried about. The limit converges. There is a limit. Right? And so this series converges by the integral test, because this also has a limit. Okay? That's really the gist of the whole deal. We're going to take the limit. We're going to integrate it, But in every one of these cases, our upper limit is going to be infinity, which means you have to solve an improper integral, which is by doing this. So anyway. All right, next one. Positive. Yep, natural log's positive, n's positive. Notice they made it start at 2, which is fine. This number is going to continue to grow, so it's definitely decreasing because the whole thing, as this grows, the whole thing gets smaller. Continuous, n can't be 0. The natural log is continuous, so we've met our conditions. We're good there. All right, so again, here's where we're going to go. We're going to take the integral of this, okay, which in this case we're going to go from 2 to b. So go ahead and tackle that one, and let's see what you come up with. All right, so yeah, going to require some u substitution here. And of course, the trick is figuring out what u needs to be, and hopefully you figured that out. U does need to be the natural log of x. This 1 over x right here is the derivative of it. So it should make it a pretty clean u substitution. So du is 1 over x dx. Well, there's my 1 over x dx. So it's pretty clean. So that's just u du. And it's important when you do u substitution. I've been noticing this on the little Facebook group that I follow. They really talk about changing the limits of integration using your u substitution, that's a tested essential knowledge, I guess. So be sure you're doing that. When I plug 2 in here, I'm going to get natural log of 2. When I plug b in, I'm going to get natural log of b. And since my natural log is on the bottom, it's actually 1 over u du, okay, which u to the negative 1, and that's just the natural log of u when we integrate this. So I end up with this natural log of the natural log, right? And this all goes to infinity. This goes to infinity. This all goes to infinity. And so there is, another thing you could say is that the limit does not exist. So therefore, the series diverges. Since the limit doesn't, since there isn't a limit, right? There is no, it is unbounded, that this will also diverge, okay? All right, last one. Positive, again, we're good there. Continuous, we can't have a 0. Decreasing, these numbers are going to get bigger. Therefore, the entire thing is going to get smaller. My upper limit is infinity, so I'm going to have an improper integral again. Okay, so the limit is b approaches infinity from 1 to b of 1 over x dx. We just did one like that, so that's pretty quick. All right, so that's natural log of the absolute value of x. Throw that from b to 1, so we're going to do that. So of course this is 0. This is infinity. Sorry, there's just this lag in the room. All right, so that limit is infinity. Again, it doesn't exist, so we would say it diverges by the integral test. Now, that's one way we could have done this one, okay? I think if we did nth term test, we would see that it diverges as well. No, nth term does equal 0, so that wouldn't, nth term test wouldn't really work there. All right, so that's the integral test. No, I guess that's the p-series test. Whoa, too far. And we're frozen. Wasn't too far. Anyway, so here's what the p-series looks like, okay? P is a positive constant. We're going to have this some number being raised to a power, okay? This is called a p-series. And as our n increases, the power on that number stays the same. This is what the p-series looks like. All right, the harmonic series is one specific type of p-series. We'll talk about that in a second. Okay, here's how the p-series test works. All right, if p, this power, is greater than 1, then the p-series converges. If the power, the p, is in between 0 and or equal to 1, the p-series diverges. It's just straightforward like that, okay? Once you realize that you have a p-series and you have it in that form, all you got to do is decide, is the power here or is the power here? And this is where we get into what's called the harmonic series, okay? And this is example 3, right? The harmonic series is when the power equals 1. 1 plus a half, plus a third, plus a fourth, on and on. And I think it's called the harmonic series. It has something to do with, there's something to do with wavelengths and musical wavelengths, and then, or something about guitar strings and how they, when you pluck a string, how much space there is in between sort of 0 and the direction that it reverberates, or to be honest, I don't know. But I know it has something to do with that. But anyway, that's the harmonic series. The harmonic series, p equals 1, that falls here, it diverges, okay? And it appears to me, through all the investigating that I've been doing, when you have a harmonic series, you can just say it diverges because it's the harmonic series. I don't think you necessarily have to say the p-series test because p equals 1. Obviously, it doesn't hurt you to say that, but I think you can save yourself a little bit of time just saying it's the harmonic series, okay? Here are some examples, and the trick with the p-series is to get it into the right form and try to recognize that. And if you can recognize that, it makes these problems a lot easier. All right, so in this first problem, the trick is trying to figure out how can I write this stuff as a power, okay? And of course, this first one is, we write this as 2 to the 1/2 power, so this is like 2 times 2 to the 1/2. And then when I sort of combine that together, I get 2 to the 3/2, add the powers, right? Same base. And then if I look at the 3, it's the same kind of deal. 3 times 3 to the 1/2, so that's going to be 3 to the 3/2. So we see this pattern. We're pretty confident now that the p, the power, is 3/2, okay? And of course, 3/2, so this is what the series actually looks like in sigma notation. And so what you do in order to determine convergence or divergence, you just have to say, okay, look, 3/2 is greater than 1. So therefore, it converges by the p-series test. And that's all you have to say, okay? And then we do the same kind of thing over here. I've got an n to the 3rd hanging around on the outside. I've got, if you remember how to convert your radicals, negative 11/3. Okay. Base is the same, you just have to add them. So this is 12/3, yeah. 9/3, close enough. Yeah, no, that makes a big difference actually. 9/3, I don't know, 12/3, it's not a 4. 9/3, okay, and then I add those together, I get 1 over n to the 2/3, because this is n to the negative 2/3. This, of course, is less than 1, between 0 and 1. Okay, so 2/3 is in between 0. It's greater than 0, but it's less than or equal to 1. So therefore, this diverges by the p-series test. So besides my little flub up here, should be pretty straightforward. Integral test, p-series test. Now I know we've thrown a lot of tests at you, and soon we're going to start talking a little bit more about what to look for and when to use what test. That's really what these next few sections are going to be about, because we still have 3 more tests to throw at you after this, and then it's a matter of putting them all together and going, okay, when do I use what?